thanked to be invited to give a talk and this conference. And as already mentioned, the topic is energy systems under uncertainty. It is a topic with which I dealt during the last, say, 15 to 20 years with different occasions and companies. Always modeling and, of course, computations played a major role. I had always different and several co-workers, so I didn't mention it here, but of course, this cannot be done on my own. Energy systems often contain uncertain parameters, as is well known and easily understandable. Demands, prices, inflows to reservoirs. Nowadays, wind speeds or sunshine are important uncertain parameters in such models. And very often in energy systems, an enormous amount of data is available. And what has to be done to understand these models is a data-driven uncertainty quantification based on a huge data set. So we discuss this in the two cases, which I would like to consider here, starting from statistical models and then until generating a set of scenarios which are inserted into the mathematical model of the systems. The two examples I would like to consider are first, electricity portfolio management of a smaller electricity company, and in that case, load and price is uncertain. And the second one, which is the main part of the talk, concerns the evaluation of gas network capacities in a large network of a German gas transport company. And here, demand is uncertain, and the aim is to validate nominations or to verify book capacities in order to sell capacity rights to customers and to transport a given gas amount through the network. Below I introduced some notions, which I will come back to this later on. Let me start with the electricity portfolio management. As I said, it is a smaller power company, namely a municipal power utility, owning several blocks of thermal power units, and all of them are combined heat and power plants, so that it can also serve heat during winter time and over the whole year electricity. And in addition to these company-owned units, the company is thinking about using the spot market for power exchange, preferably the European Energy Exchange. And in order to hedge against risk, they also thought about, at that time, to buy and sell futures, electricity futures, in order, as I said, to hedge against uncertainty. Of course, they have to serve the customers with electricity and heat, and here you can also see different versions of demands, right? So once again, the portfolio of such a company consists of the power production based on company-owned units. In addition, they have to look at bilateral contracts. They have to decide about which of the contracts they would like to use. the aim at using the spot markets for day-ahead spot market trading and to hedge against risk the trading of electricity futures. The time horizon is 1 year with an hourly discretization. This means the model is large scale. A year has 8,760 hours. So this is the time discretization. For each hour, there are a number of decisions. So the model is really large scale, also already in the deterministic case. But we are in a stochastic situation due to the stochastic load and price process. Over a year, there is a lot of uncertainty. It's completely clear for the spot market prices, but also the load is uncertain due to weather uncertainties and many other things. As I said, we would think about modeling such stochastic processes first via a statistical model and later an approximate representation by a finite number of scenarios. The aim is, or the objective is, to maximize the total expected revenue for the company, but also to minimize eventually the risk of decisions. From a mathematical point of view, the model is what is known as multi-stage stochastic optimization problem. It is mixed integer in general because the blocks can also be switched off and on, so 0-1 decisions, and it is extremely large scale. To have a look at typical time plots of load profiles, which is the upper picture, for 1 year, we have 52 weeks. You see the demand is higher during wintertime and lower during summertime, as typical for Europe. It's different in the US, but in Europe, this is a typical picture. The lower picture is a typical spot price profile for 1 year with these peaks, price peaks, which are due to power outages, unit outages in Europe in an interconnected system. So there are a number of really high peaks of prices. Let me start with the statistical model and the generation of scenarios and scenario trees. So the first step is that one has to check the data, and it turned out that the daily averages satisfy a normal distribution. Hence, we thought about fitting an ARMA model, and since we have 3 parts, namely heat demand, power demand, and electricity prices at the spot market, it is a 3-variate ARMA model, and this is fitted to the daily averages. In addition, we looked at the intraday profiles for demands and prices and developed certain clusters of possible intraday behaviors, which is later used and to sample from such clusters for the final representation of the process. So when we think about generating scenarios, we of course started with the time series models, this ARMA trivariate ARMA model, and we generated first scenarios from this model. We are Monte Carlo, or nowadays we are quasi-Monte Carlo samples from the multivariate normal distribution. Daily means that we have a dimension of 365 dimensional multivariate normal distribution. So it is not a small problem. And in addition, we added deterministic trend functions and finally also matched intraday profiles. We sampled, as I said, via Monte Carlo or quasi-Monte Carlo, a number of scenarios. and finally generated a tree by a specific method which is based on recursive scenario reduction. I come back to this in the second part of the talk. So this is a typical scenario tree which we used, and we have monthly branches since these electricity futures have a monthly time horizon, and so these branchings are somehow adapted to the behavior of the financial behavior of the futures. Okay, what is the objective? As I said before, we would like to maximize the expected revenue, overall revenue, and possibly also minimize the risk of decisions. The question is which risk measure. I do not want to talk about risk measures in details. This is a topic of Andrzej Roszyński's talk tomorrow morning. So we used a particular risk measure. It is of aggregation type, and it is based on the average value at risk applied to the minimum of the stochastic revenue process evaluated at certain risk measuring times. So we decided to look at 52 so weekly risk measuring times, and they correspond to the last time period before the last offer to the spot markets in the last trading day of each week. So this is the risk measure which is used. And when looking at such risk measures, the efficient frontier is always or often considered, which means that we look at the behavior. In our objective function, we had such a parameter gamma, which varies in the interval 0, 1. So gamma equal to 0 corresponds to risk neutral case, so no risk measure included. And gamma equal to 1 means we only minimize risk and do not look at maximizing the expected revenue. And when we vary this gamma between 0 and 1 and look at the pairs of the risk measure at the optimal revenue process and also take as a second component the expectation of the revenue at the end of the time horizon, we get a certain curve which is known to be concave in that case. And the interesting effect is, so we had a number of computations to perform. The models had 2 million decision variables, but it took only 1 hour with the version of CPLEX we used at that time to arrive at optimal solutions. And it turns out that the risk aversion doesn't cost too much. The costs are less than 1% of the expected overall revenue. So it is recommendable to include a risk measure, and the losses are not very high. Okay, here are some final pictures. These scenarios in tree form are here given for the risk neutral case. So the obvious effect is that they are, at the end of the time horizon, very diversified with a high fluctuation in between. And this is due to the fact that we didn't include a risk measure in that case. The picture is completely different if the risk is also included. And then at the end of the time horizon, all scenarios get very close. So the variance is now very small compared to the risk neutral case. But this is due to the fact that excessive future trading is done or has to be done by the company. And that is what is completely different from before. Here's no future trading, but hedging against risk requires trading of futures. So this is one example. Hopefully I lost not too much time. I did. Second example is looking at a gas network and to evaluate gas network capacities and to look at what is called in this business validation of nominations. The largest company in Germany has the name Open Grid Europe, and the OGE for short. And it is, as I said, Germany's largest gas transport company. And the network is very big and involved, and it consists of intermeshed pipelines which are actuated and safeguarded by certain active elements. There are many of them, like valves and compressor machines. Here we concentrate on the stationary case and the isothermal case, which is, of course, an ideal situation, but even in that case, it is a difficult problem. There are two types of gas which are transported in different networks, the so-called H gas and L gas, which means high or low calorific gas. And the gas dynamics is the main difficulty. It is, in a pipe, is modeled by the so-called Euler equations. They are nonlinear system of hyperbolic partial differential equations. In the stationary case, and the isothermal case, the very complex hyperbolic partial differential equation system boils down to nonlinear relations between pressure and flow, but this nonlinearity cannot be avoided. And hence we arrive at a large system of nonlinear equations and inequalities, which also contain integer decisions due to the fact that the compressor machines can transport the gas in this or the opposite direction, sometimes also three situations. Hence, it is a very nonlinear system. The aim is to evaluate the capacity of a gas network and to validate a nomination, or even to verify book capacities, which means that a certain customer is interested that a certain amount of gas is transported to a specific exit of the system, and the company has to decide whether this is possible in addition to all the other capacities which are moved through the system, and hence certain computations have to be done, which means certain nominations have to be validated, and in general the capacity of the network has to be explored. To give you an impression, this is the gas transportation system in the whole of Germany, and now we look at the transportation system of Open Grid Europe. The red parts correspond to the so-called H gas, and we have two parts, namely the upper part is the H gas north system, and the lower part is the H gas south, which is a more involved model. Also the network is more involved. And the green part is the L gas networks. And all of them have to be looked at and have to be explored and studied, and capacities have to be evaluated. Let me give you a short idea what has to be done when generating, again, scenarios for the underlying stochasticity, which is here related to the uncertain load or demand at the network exits. In both cases, H gas and L gas, these are hundreds of exits, Hence, the stochasticity is again very large scale. So for the L gas, we even have 700 exits. So the multivariate distribution has dimension 700, which is really large scale. Again, we have a huge amount of data. We have hourly gas flow data at exits for the previous 8 years. And since we are interested in the stationary behavior, we look at the daily mean gas flow only, and but at all exit nodes. And since it depends on the daily mean temperature, we also consider a so-called daily reference temperature, which is based on a weighted average temperature taken at different network nodes. The company has a certain idea how to compute such a daily reference temperature. The stationary and isothermal modeling requires to introduce certain temperature classes, as they are noted here on the slide, and we perform a certain filtering of the data according to these temperature classes, and in such a class we are almost isothermal, say, and hence we have to reorganize our data set, which is a certain amount of work and takes some time. And a special treatment is required for the low temperatures. We will come back to this. The picture below shows you the temperature classes in a certain point cloud of such data set. These are typical situations of the data for daily mean gas flow at exit nodes. The upper three parts correspond to certain small power stations, and below you have examples for gas flows which is used by a company, or which corresponds to a market transition point, or to a gas storage, which is also included into the network. After revisiting or visual check of the data, we finally decided to consider these type of distributions, namely uniform distributions, also shifted situations, because we realized that a lot of null zero flow happens in several exits, and also we considered the shifted normal or log normal distributions. All of them appeared in a number of situations for the exits. So we had, in particular, such an example like there. This is a shifted normal distribution function. It happened that also multivariate normal distributions became important, because we realized that in case that the normality tests are satisfied, there were significant correlations to other exit nodes, preferably or very often to those exits which are close to a given exit. And here is a picture for a part of the exits which satisfy certain multivariate normal distributions in certain temperature intervals in certain areas of a specific network. This happened for all three networks, L gas and H gas, and in all cases it was different, of course. Low temperatures. For low temperatures, we typically have a lack of data. What to do? The idea is to look at the whole point set and to introduce a regression based on penalized splines satisfying certain shape constraints. So what we did is a least square regression based on cubic splines in a B-spline basis representation, and we optimized the coefficients of the B-splines. The other two parts take care of certain shape, so they are smoothing and took care of certain behavior of the splines at the end of the time horizon, for example. And this is a typical point cloud. The curves below corresponds to the B-splines, and the curve which came out here is the black one. It corresponds to the penalized spline estimate based on this method. The red curve is a sigmoid regression, which is a nonlinear regression, which is non-convex also. So it was a better idea to use the other one based on splines. Okay, scenario generation. How did we do it? We started with Monte Carlo or quasi-Monte Carlo estimates. In our case, we looked at so-called Sobol point sets, but we looked at random scramblings of such Sobol sets because it led to excellent multidimensional point sets in the unit cube. Then they were transformed via univariate distributions in the inverse distribution sense. And finally, in the multivariate case, we looked at decompositions of the covariance matrices and preferably based on principal component analysis, and performed the standard way of transforming everything to the uniform situation in the multidimensional case. Here is a picture for 128 Monte Carlo samples generated via the possibly best pseudo-random number generator nowadays, the Mersenne twister, in the comparison with the scrambled Sobol point set. So you see that's much better than the, on the left, the Monte Carlo set. Okay, and finally we performed a certain optimal scenario reduction, which is described by this picture. So we started with 1,000 samples via quasi-Monte Carlo Sobol point sets, and finally selected a certain smaller number here, 50 scenarios, which fitted very well to the 1,000 points before, in the sense of a certain probability metric, here the Kantorowicz distance. Okay, this is the conclusions slide finally. I do not read again what the steps were. We started with data analysis, filtering of data, introducing temperature classes, had a special treatment for the low temperatures, and finally used randomized quasi-Monte Carlo methods to generate scenarios. There is a book which appeared this year in the MOS SIAM series on optimization. The editors are 4 members of our team. We were about 30 mathematicians in Germany dealing with this topic, and it is called, the topic of the book is Evaluating Gas Network Capacities. There is much more in this book than what I presented here, also the optimization part, but our part is also in. Thank you very much.